So hello everyone, welcome to Temporal Graph Reading Group today. So we are very glad to host Veronica um, from the Arctic University of Norway, and then for longtime audience of the reading group, you also know that that's not the first time that Veronica has presented here, and we are very excited to host her today to talk about their recent work bridging theory and practice in link representation with GNNs, which was presented at NeurIPS 2025. And more information about our speaker today. So Veronica Lachi is an associate professor in the ML group of UIT, the Arctic University of Norway, and her research focus on the expressive power of GNNs, uncertainty quantification in graph learning, and learning on graphs with missing data. And I will pass the mic to you, Veronica.
Thank you so much, Andy, and thank you very much for having invited me here. It's always a pleasure to present work here. And yeah, as you were saying, I'm going to present this work. So first of all, I'm going to share my screen. Can you all see my screen?
Yes, yes, we can see your
Okay.
screen. Yeah.
So this work is bridging theory and practice in link representation with graph neural networks. So I've worked on this project together with some collaborators from University of Trento, from Fondazione Bruno Kessler, and also from University of Aalborg. And yeah, so as many of you knows, there are a huge literature on expressive power graph neural networks. So usually in general, in deep neural networks, there are some works that investigate the universal approximation capabilities of neural networks. So usually a key theoretical question for these works is are neural networks, so are such type of architecture universal approximator? And based, of course, on the different kind of neural networks, there are some different works and results. So, for example, it's well known that multi-layer perceptron can, under some mild assumption, can approximate any function arbitrarily well. So when coming to graph neural networks, some people asked sort of similar question like, are graph neural network able to approximate some kind of function? Other people ask a slightly different question, but more or less the theoretical aim is the same. So the question is, for which kind of input is the graph neural network able to produce different outputs? And so the important thing is which kind of input. So graph neural networks, with graph neural networks, we can perform several different tasks, supervised tasks, like for example, node level tasks. So we can have one big graphs with several nodes, and our aim is that of approximate a function that goes from the set of nodes and the topology to, for example, a set of classes or a real value. But we can have also edge level prediction. Like for example, we might be interested in approximate a function that goes from a set of links to a probability score, or for example to a real world real value. Finally, we can also be interested in performing some sort of graph level task. So, for example, we can approximate function that goes from a domain of several graphs to classes. Okay, so in general, with graph neural network, we can tackle several different supervised tasks. And so far, the expressiveness of graph neural network have been widely studied from a graph level point of view. So there are many results about for which kind of graph can a GNN produce different output. While, for example, the edge level and the node level study of the expressiveness is less studied. And that's what we wanted to do in our work. So first of all, just a brief recap of what expressiveness on graph level means. So, as I was saying before, when we talk about graph level prediction, we want to approximate a function that goes from a domain of graph to, for example, an embedding space. So in this case, when we study expressiveness, we are not interested in the final class, for example, or the final regression value, but we are interested in the representation that we obtain for a graph, for an edge, or for a node in the embedding space. Okay, so what we obtain, let's say, with the encoder. So before the final decoder that can be for classification, regression, and so on. Ideally, what we want is that the map that we approximate with the graph neural network is injective, meaning that if the two representations for two graphs are equal, then the starting graphs are equal. But what does it mean to be different or equal for two graphs is a little bit more difficult. So different embedding is quite easy to understand, while what does it mean to have different graphs? So, for example, you can have some examples when you look at the graph and you are not able to say, yes, these graphs are equal or not, or maybe you say, yes, these graphs are not equal, but actually they are. And so, for example, this graph is equal to this graph, and this graph is equal to this graph, even if you look at them, maybe you can think that they are different. So basically, when we are talking about graph level task, two graphs are equal, whether they are, if they are isomorphic. I don't want to enter in the detail of the mathematical definition, but the important things is that basically two graphs are isomorphic is if they have the same structure up to a relabeling of nodes. Assessing whether two graphs are exactly isomorphic can be quite hard, and usually we resort to some sort of computational lighter way of assessing whether two graphs are isomorphic or not, in particular the Vas-Farrell-Lehmann test. So the Vas-Farrell-Lehmann test is an iterative procedure to test whether two graphs are equal or not, and the test is not perfect, meaning that there are some cases where the WL test tells you that the two graphs are equal, but are different, sorry, but actually they are not different, okay? And it is well known in literature that graph neural networks are at most as powerful as the WL test in distinguishing between graphs. And this is because basically the GNN and the WLTS are the mechanism are, let's say, sort of the same, but in the WLTS the hash function is injective, while in the GNNs not always the combine and aggregate function gives rise to an injective function. And so basically we can match the power of graph neural networks and Vas-Farrell-Lehmann tests if we are able to have some sort of injectivity in the combination and aggregation function. And this can be quite easily reached by some trick that I don't want to enter in the detail, but you just have to know that is it possible to have graph neural networks that are as powerful as the WL test. As I was saying before, there are some failures, however, of the Vas-Farrell-Lehmann test. So some graphs that, okay, you want these graphs to be distinguished because they are not equal, but the Vas-Farrell-Lehmann test tells you that these two graphs are equal. And so the same holds for a GNN. Given this, many more powerful graph neural network based methods have been proposed, like for example, K-GNNs. There are graph neural network that doesn't look just at the neighborhood, but they consider higher ordered interaction between nodes. The problem is that many times these kind of more powerful architecture are, let's say, a little bit computationally expensive. But the interesting point is that in literature there is a sort of hierarchy of the existing models that are more powerful than the graph neural network. So many people have produced new architecture, and given this hierarchy, it's possible to say, yes, this method is more powerful than this other, and so on and so forth. Okay, so let's go into the details of what we did. So far it's just a brief recall of the literature. So we asked, okay, but what about the link? Because so there are so many results on the ability of graph neural network in distinguishing graphs. There is this hierarchy of methods. What can we say about link? Because you might think that in graph neural network, one very important application is link prediction, for example, which is very important, for example, for recommender systems and so on. So we asked how expressive are graph neural networks in distinguishing between these links. And so, as I was showing before, when we deal with a graph neural network for link level prediction, we have that the graph neural networks approximate a function that goes from pairs of node to a representation, okay, where these pairs of node, of course, can be an existing edge of the graph or even an edge that doesn't exist, so just a pairs of node. For example, you may want to predict whether this link that is not observed in the graph is actually in the graph. Okay, so for example, you may want to predict whether two users can be connected in a social network or whether a customer will buy a certain product at a certain time. Okay. Even in this case, ideally, we want this map to be injective. So we want that if the two representations for two pairs of nodes are equal, then the original links were equal. And even in this case, and assessing whether two representations are equal, it's quite easy because we just have some embeddings and we can compare them. But it's not so easy to understand whether two links are equal or not. So for example, if I give you this graph, and I give you, for example, the link VU prime and the link VU, I want to know if these two links are equal or not. So it's not that easy to understand whether these two links are equal or not. Some of you may answer, well, these two links are different because, for example, between V and U prime, there is one common neighbors, while between V and U, there are no common neighbors. Or maybe some of you can say, well, these two links are different because the shortest path between V and U prime is 2, while the shortest path between V and U is 4, for example, okay? So these are possible answers. And of course, there is a mathematical formalization of this, which is strictly related to the automorphism on graphs. So even in this case, I don't want to enter into details. But basically, an automorphism is a permutation of the node that maintain the adjacency matrix of the graph the same. So for example, if you take this graph here, you can see that basically there is a sort of axis of symmetry in this graph, which is the dotted lines that I drawn here. And so you can think that basically if you exchange node 0 with node 2, node 1 with node 3, and you keep fixed node 4, this graph basically stays the same. And indeed you can see this, so you can exchange in the adjacency matrix the first row corresponding to the 0 node and the second node, and if at the same time you also exchange node 1 and node 3, and you keep fixed node 4, then you end up with an adjacency matrix that is exactly the same as before. Okay, so basically this automorphism is just a way of viewing some sort of symmetries, axis of symmetries in the graph. Okay. So, given this definition, we can say that two links are automorphic if it exists an automorphism that at the same time exchanges the two endpoints of the link. So, for example, if you look at this graph here, you can think about the axis of symmetry that is kind of a sort of mm, line that goes from U prime to U. So you can exchange U prime and U, of course, but at the same time, if you want to use this automorphism that exchange U prime and U, you also have to exchange V with this node here. So it doesn't exist any automorphism that exchange U prime and U, keeping V with V. Okay? So the answer using this formal definition of what does it mean for two links to be equal or not, the answer is that these two links are different because it doesn't exist an automorphism that exchange at the same time the two endpoints of the link. What is the problem of normal GNNs? So usually GNNs for link representation are made like this. So you take the endpoints of the link calculated by the GNNs, so basically the colors of the Westphalian element test, and then you make a way, you find a way to aggregate these two endpoint representation. Like for example, you can use an MLP on the concatenation, you can do a dot product or whatever. But the problem is that GNNs are not able to distinguish between not automorphic links, which are composed by automorphic nodes. So again, I want to show another example, which maybe it's easier. So consider this graph here, and you can imagine that you have a axis of symmetry, a vertical axis of symmetry here. So it does exist an automorphism that exchange U and U prime, But at the same time, these automorphisms also exchange V with this node here. So basically, it doesn't exist an automorphism that exchange this and this and keep these fixed at the same time. So even in this case, U and V, it's different from V and U prime. But these are the color produced by the Pascal element test. So basically, with a standard GNN, you are going to produce the same representation for link UV and VU prime. Okay, so no matter which complicated function do you use for aggregate these endpoint representations, you will end up with the same representation for these two links, and so this is translate also in the same probability of existence. And this might be a problem, for example, from a social network point of view. It is well known that usually it is more likely to have a link that closes a triangle. So, for example, one can expect that this link here is more probable than this link here, okay? But with a standard GNNs, you end up with the same representation and thus with the same probabilities of existence. Okay,
So a quick
yeah,
question, if you don't
yes,
mind.
yes, of course.
Yes, yeah. So so that's a great analysis of the GNN and
Mhm.
how they work with node embeddings. But there are also more specialized model that directly generate a link level embedding that never generates a node embedding. So what is the implication of that? So for example, something like a graph mixer that you might be familiar with. So like link native models then
Yeah.
they would not have this kind of issue, or would they be more powerful or less powerful, or what do you think?
Yeah, it depends. So, for example, if you one can think about transforming this graph into the line graph, okay, and
Mhm.
performing like link prediction as a sort of node classification in line graph, and it has been proved that this is more expressive. So, if you have some sort of models that perform directly, that calculate directly the representation of the link, you can have something better. But of course, it depends on how this representation of the link is calculated, because in some other cases you have the same problem. Okay, so it really depends on the model at the end. And yeah, so
Mhm.
later I also will show you some example of this, and yeah, try
Mm.
to show you also. So the aim of our work is exactly that of trying to understand a sort of hierarchy of expressiveness between different methods, not just the normal GNN, basically.
Mhm. Okay, thanks.
Thank you. And yeah, so as I was saying, so this is a problem of normal GNN, and also as Sandy was saying, there are some methods that try to overcome this limitation. One example is that of using, for example, method that directly calculate the representation of link. I reported here some examples, and in the paper you can also find the references of this paper. So, for example, these are some very famous methods which overcome this limitation. So all these methods that you see here, they don't have the problem that I showed you before in the example graph. Okay. So, for example, NCN doesn't use just the representation of the endpoints of the link, but it uses also an additional representation, which is the representation produced by the GNN of the common neighbors, first order common neighbors. ELF, for example, is another method that consider also the count. So in this case, it's important not the representation, but the count of higher order common neighbors. Or for example, you can have NeoGNN that uses path, or SEAL that produces directly a representation of a subgraph of the link for which you want to calculate the representation. Okay. So these are just a bunch of examples which are famous, let's say, but there are many. And in general, what all this paper claims is that they are able to overcome the limitation of before. But what we asked is, okay, there are some these kind of spot works that try to overcome this limitation, but is it possible to really understand the hierarchy of the expressiveness of these models, and in particular to assess whether which component of this model is more important for having at the same time expressiveness but also good computational cost? Okay. So what we did is we create a general framework under which all the most famous existing link representation models belongs to. So basically, all the method in literature can be rewritten using the framework that we proposed. So the framework, the notation of the framework, let's say is quite heavy. So I just want to briefly show the main component. So basically, every method that produce a representation of link UV can be expressed as a combination of parts. One part is the endpoint representation. So you take the endpoint of the nodes and you calculate some representation using a message passing function that has some expressive power. Like for example, this can be 1WL, 3WL, and so on. Then we have another part that is the neighborhood representation. So representation of nodes in a certain order of the neighborhood, where this order is encoded with this parameter m. This representation can be calculated with some layers, message passing layers. So we have another parameter which is the number of layers used and the powerful, even in this case, of the message passing use. So 1WL, 3WL, and so on. So one important distinction is that some of the work consider a representation produced by some layers of the message passing, like for example NCN. Some other works, like for example ELF, basically they just count. So this is like having a message passing layer basically with zero layers. Okay. So basically here you can see in the table all the instances, all the model that exist in literature with the instances of all the function that we identified in our general framework. Why is this framework useful? Because, okay, it encompasses all the existing method, but also possibly new one. And because it enables us to study the expressiveness of all the method in a unified way. So we were able to prove this theorem. This is like informal, but for the formalities, you can see the paper. So basically, we prove that the higher m plus l, the more expressive the model. But this is important because basically what we can say is we can increase l instead of increasing m. Why this is important? Because increasing m usually bring higher computational complexity. And so basically what we say is, okay, if we want to have more expressive method from a link representation point of view, it's better to use the representation of the node calculated with some L layer message passing with respect, for example, to the count of common neighbors. And of course, this also brings a sort of trade-off because you know that increasing L can lead to, for example, over-smoothing and so on. So of course, this you can increase it, but not as much as you want. But then, so the point is that it's enough to have this that is a little bit bigger, like for example, 2 or 3 layer, and keeping M very low, like for example, 1, so first order neighborhood instead of considering, for example, higher order neighborhood, but just counting the number of common neighbors without using their representation. And then we also prove that the higher the expressiveness of the raw model, so the model that deals with the neighborhood nodes, the more expressive the model. So basically, this implies that it's useless to increase the expressiveness of the model of the endpoints node. So it's better to, if you want to, like, let's say, increase a little bit the expressiveness of one message passing model, it's better to increase the one that operates on the neighborhood. So this is just a theorem, and based on this theorem, we were able to produce a hierarchy of the existing model. So based on the specific instances that the existing model have on M, L, K rho, and K phi, we were able to produce a hierarchy, which is this one that we show here. And based on this, we also perform a synthetic experiment. So basically, we design the first synthetic data set for link representation, for expressiveness of link representation. So basically, the data set is composed by several graphs, and within each graph, there are links which are not automorphics, but composed by automorphics node. So basically, links that are very difficult to be distinguished by a normal GNN. And you can see that basically, even in this synthetic protocol, the hierarchy is the same that we produce with our theorem. So all the base GNN models are not able to distinguish any links. And then this hierarchy is respected even in the performances. So basically, SEAL, which is the most expressive model for our hierarchy, is also the one reaching the highest test precision in our experiment, and so on. So this is completely theoretical from an expressive point of view, but we also asked, okay, but is this expressiveness really useful when it comes to link prediction? So far we have talked about producing a representation of the link, but in real world task we have link prediction. So do we care about having such expressiveness when it comes to real world application in link prediction? So what we did is, first of all, we calculate a metric that tells us how symmetric is the graph. So we can calculate it by using this exact formulation, where this number here is the number of orbit of the graph, where with orbit I mean the partition induced in the vertex set by the automorphism of the graph. So basically, it's how many equal nodes are there in the graph, where equals means that they have the same structural rules. Then I will go a little bit more into the details of this. So this is a formula for assessing how symmetric is the graph. Calculating this is quite computationally expensive because calculating the orbit is computationally expensive. So we use a approximate version of this, where instead of the orbit, we use the number of colors produced by the Weisferrer Lehmann test. So basically, you can imagine if you have a graph that is every node has a very different structural role within the graph, you can think that the Weisferrer-Lehmann test produces different colors for all the nodes. Okay, so in very asymmetric graph, the number of nodes and the number of Weisferrer-Lehmann colors are equal. Okay, while if you have a very regular graph, very symmetric graphs, the number of colors is few, and then you have that this level of symmetry is higher. Okay. So what we did is we ordered the existing benchmarks for link prediction from the least symmetric to the most symmetric, and we also ordered the existing models for link prediction from the least expressive to the most expressive. And basically, what we saw is that this such high expressiveness it's needed just when the graph is very very symmetric. Okay, so actually I have to say in few cases. So when you have very asymmetric graphs with possibly a lot of different features, original features in the node, basically all these expressiveness is not needed because a normal GNN that has the problem that I showed you before is anyhow able to reach very high performances in normal dataset. So this is a sort of we were trying to give some hint for model selection. So there is not always important to select the most expressive model. In many cases, you just have to you can just use a normal GNN for link prediction. You can use expressive model that are more computationally expensive when it's needed from the data. So when you have very symmetric data set and you can calculate the symmetry of the data set. And so you can decide which model to use based on the data set at hand. And yeah, this is also related to some other important works that are coming up now regarding the role of expressiveness together with the generalization. So many people highlight the fact that it seems that being more expressive comes at a cost of being less able to generalize. So we always have to ask while we are studying expressiveness if this is useful for our data or if it can also hurt somehow our task at the end. So yeah, this is also for future direction for many of us that are studying expressiveness that of try to also consider other factors and not just the expressiveness. And that's it. So thank you very much. And if you have any question, you can ask me, or if you have some other question in the future, you can also send me an email.
Yeah, so I do have some questions,
Yeah.
but if there are some questions from the audience, feel free to pitch in as well. Can you go back a little bit to the earlier slide where we were talking about the expressive power, like the intuition part of M and L, I think? Just trying to
Yes, yes, of course. This one here. No, sorry.
the next one.
Yeah, here.
Yeah.
Yeah.
So M is the message passing. Sorry. The M is the number of joint neighborhood. Uh,
Yeah.
the okay, and then L is the number of GNN layer, right?
Yeah, exactly. M is the order of the neighborhood that you consider. So, for example, you can consider first order neighborhood. So here you are going, for example, to consider
Uh-huh.
this node here and for this link and no node for this link. But if you increase M, you're going to consider second order neighborhood. So for example, you consider the second order neighborhood or third order neighborhood, common neighbors, and so on. So basically, there are some methods that try to increase as much as possible this M here in order to be more expressive.
Right.
Okay. But the problem is that this is very computationally expensive. And so what
Mhm.
we found out is this is not necessary. So basically, it's better to consider just the first order neighborhood, but considering the representation of this given a certain number of layers. Because basically, it's doing the same. You are going farther, but not counting, but using the representation. And
Yeah.
this is it's less computationally expensive to use a GNN layers with L, with a hope of L, with respect to considering an higher order neighborhood, basically.
Okay. And then also the K, just the one
Yeah.
just below it, the K is what exactly?
Yeah, sorry. Yeah, the K is the expressiveness of the message passing model in terms of graph level. So, for example, this can be one WL powerful as the one
Ah, I
WL,
see. I see.
or the 3 WL, 4 WL, and so on and so forth.
I see. I see. Okay, that's interesting. I'm just trying to understand this
Yeah.
in terms of generally, like, what is the implication of this for, let's say, you're trying to build graph foundation model, because
Mm,
let's say, I mean, like much of the field are trying to build graph foundation model for the past few years, right? And people are
yeah.
thinking, can we have a model that works best for all the tasks that we want to do, graph, link, and node? And
Yeah.
then what this means is that you will likely need a specialized link model, and
Mm.
expressiveness for different level of tasks should also be separated out and understood separately, if that makes
Yes.
sense.
Yes, exactly. This is also, there is another paper actually, or I don't remember anymore the name, but quite, let's say, also old paper. It was not on graph foundation model, but on graph level.
Yeah.
And in this paper, there was this concept that basically the standard GNNs are very good for graph level and node level. And it's okay.
Hmm.
So graph and node level, you can tackle them together, basically. But when it comes to link or even subgraph level, it's something like, it's a little bit different. So in order to work well with this subgraph level, so link and other stuff, it's better to reason in another way that is not the same as for graph level or node level, basically.
But this is kind of counterintuitive, right? Because subgraph is essentially the same as graph level, but you just cut out part of the graph, right?
Yeah, but it's like, okay, let's say that GNNs are working mm, node for node level, so you're going to produce representation for node level, so this is cool. And then when it comes to the whole graph, you just aggregate together all of this and it's cool. But it's like I don't remember anymore the exact content of the paper, but it's something about it's something like they are not able to really learn the distribution of something that is in the middle. I don't know how to explain, but I can also link the
Interesting.
paper to you. I can find it again. And I know that it's a little bit counterintuitive, but it's something related to learning the distribution of stuff, basically.
Interesting, interesting.
Yeah.
Yeah, and thanks for the discussion. I'm also wondering if this is because technically, if you think about graph level task and node level task, it's actually doing a different task than link level task. Because link level task, you think about link prediction, it's doing a matrix completion task, while the
Yeah.
node and
Yeah.
graph level are essentially doing some coloring task, essentially.
Yes, exactly. Even, yes. Yes, even
So
this.
the type of the task is also different. So
Yeah. Yeah.
so I'm more thinking on a high level, is there even hope to try to build a universal
Hmm.
function approximator over all type of task on graph for something else like you know like something you have like the image encoders
Hmm.
for the CB side. Can we do the same for the graph side, or that is there's no hope of achieving that? You should really just have separate specialized general models for each type of task. So I think.
Yeah, actually, yeah. I don't know because I was also thinking that yeah, as we showed with our last experiment, okay, this is a problem, but maybe not in all. So it also depends a lot on how informative, for example, are the feature of the pairs or of the
Mhm.
subgraphs. So maybe many times the features are not enough, but are very informative. So maybe you don't care if maybe with some specialized model it's better for some very specific case, but for others I have this feeling that maybe it's enough to use the to combine together representation of nodes basically. So I think that really depends on the task and on the symmetry of the graph. And yeah, so I don't have a proper question, an answer, but yeah, I think it's worth it to also investigate on this regarding the foundation model, let's say, even more important, let's say.
Mhm. Yeah, thanks. Yeah, and
Thank
thanks
you.
for the nice presentation and sharing your thoughts. Are there any questions from the audience or any follow-up question to that? No? Okay. If not, we can also wrap up the talk today and thanks so much for presenting your paper, Veronica.
Thank you. Thank you so much for inviting me.
Thank you. Yeah, and thanks for sharing it here. Yeah.
Thank you.
Yeah. So then see you everyone. Yeah. Thank
Bye
you.
bye. Thank
Thank
you.
Bye.
you.
Bye.
Bye.
Bye.